Okay, so we're going to look at a rotational statics problem. In other words, here's a meter stick, 10, 20, 30, 40, 50, 60, 70, 80, 90, 100 centimeters long. So each one of these lines represents 10 centimeters. Here's a meter stick, and it's going to be, we want it to be in equilibrium. It has a 4 Newton force pulling straight down at this end. It has an unknown force, so I don't really know how long the arrow is, so take that with a grain of salt, of force 2 over here. It has, and this is an important, very important point, for any object, its weight always acts on its center of mass. And since this meter stick is uniform, its center of mass is right here in the middle. If something isn't uniform, think of the baseball bat or club or whatever this is, its balance point is closer, is not right in the middle of the bat, it's closer to the heavy end. And that's where its weight would act on. So the center of mass is where the weight acts. And so the weight of this meter stick is going to be, well, we'll just do this first. We'll just draw it. It's going to be mg of the meter stick, which will be, m is 0.398, so 0.398 times 9.8, all right, comes out to be 3.9 newtons acting at that spot. We want to put a 12 Newton force somewhere on this meter stick, either acting up or down, to make sure it stays in rotational or equilibrium, so that it doesn't rotate, just stays right like that. So we don't know where to put this 12 Newton force. You may also be wondering, but I don't know this force. I got two things that I don't know. This is what makes a statics problem in rotation a little unique. Since it's static and not obviously rotating around anything at this point, you can choose the axis of rotation to be anywhere you want. Which brings us to another very, very important point. Any force that acts on an object, so it doesn't have to be a meter stick, it could be any object, it could be a rectangle. Any force, say this is the center of mass of that object, any force whose direction is directed through the center of mass cannot make the object spin. It can only make it move translationally. So a force that comes at this and pushes here in line with that center is just going to move the whole thing that way. It's not going to rotate it. Now this force here, that doesn't go through the center and it will rotate it and also move it translationally. So any force that acts at the axis of rotation, so this goes for the center mass, it also goes for the axis of rotation. Let me clarify that. If an object isn't pinned down anywhere, it will rotate around its center of mass. Let's say we take this board, right, and we pin it down on a table so that its axis is now here. So here's its center of mass, but this is the axis. Now, any force acting on this point will not cause it to spin. Now this would, because this is the axis. If the object is just floating in space, then it will always naturally rotate around its center of mass. So there's a slight difference there. But here's the cool part. Since it's in static equilibrium, I can choose the axis to be anywhere I want. And so what we do is oftentimes you'll be missing a force. Guess where I'm going to put the axis? If I put it here, at this end, that force doesn't produce a torque. It is not a force I have to worry about now in terms of rotational equilibrium. So I can eliminate that by putting the axis here. So a smart placement of the axis can help you quite a bit. So if this is my axis, I need to know the torque by this and the torque by this so that I can figure out what torque I need. Because if that's my axis, both of these are trying to rotate it this way, clockwise. So I'm almost guaranteeing you that my 12 Newton force has to be up to counteract that. So let's figure out what the current net torque is by these two. So the torque by this is going to be this value of the force times 2, 3, 4 times 0.5. So the torque by the weight of the stick is going to be the force. Well, we'll use the lever arm first, like the equation. So it's going to be 0.5 meters. That's the distance from the axis to here, times 3.9 newtons. And then over here, the torque by force 1 is going to be, well, it's a full meter, so 1 meter times 4 newtons. So the torque here is 4 newton meters. The torque here, let's see, times 0.5 is 1.95. So is, and by the way, I'm going to call them both negative. So torque here is negative 1.95 newton meters. Why negative? Once again, if this is my axis, these are, they're both trying to rotate this thing clockwise, which is negative. All right, so I need a 12 newton torque, a torque with a force of 12 newtons that will equal the sum of these two. Because I need the net torque, if it's going to be in equilibrium, to be 0. That means the torque by, we'll call it force 3. We'll put the minuses in here. Minus the torque by the meter stick, minus the torque by force 1, should add all up to 0. So I know I put a negative sign here. Don't duplicate it. Don't bring the negative sign down here. We'll just let this take care of that. So I need, bottom line is torque 3 needs to equal the torque produced by the weight plus the torque produced by force 1. We can even say their magnitudes need to be equal and just clarify that. So what do we got here? Well, I got 1.95 Newton meters plus 4 Newton meters. So I have 5.95 Newton meters. Over here, I know the force, that's 12, but I don't know R3. I don't know how far I'm going to place it. So if I divide both sides by 12, so if I take 5.95 divided by 12 newtons, then it tells me I need to place it at 0.496, so darn near the middle point of this, actually. So it turns out that I need to place the 12 newton force, force 3, 12 newtons. I need to place it here to keep this thing from spinning. Now, if that's the case, the next question is, well, what about that force? What about this missing force up here? Here's what we do. If this thing is in truly completely static equilibrium, it's not accelerating up or down or left or right or anything either. So that means the sum of all the downward forces need to equal the sum of all the upward forces. And that's interesting then, because I'm in trouble, because that would give me 3.9, that's almost 8. I already got 12 here, so this force actually should be directed downward. Because, right? Because this would be 3, this would be about 8 down and 12 up, so this would have to be about 4 newtons down as well over here. So my arrow was in the wrong direction. It didn't matter for rotation because I made the axis there, but when I look at translational, when I do the free body diagram, I got 1, 2, 3, 4 forces. These 2 down add up to 8. I got one of them that's 12 up. So I got to make it in equilibrium. I got to have another 4 or so down. So my arrow was in the wrong direction. You'll forgive me. But that's kind of a side thing. The important points to note are that static situations, you can place the axis anywhere, and there's usually in a problem a good place to place it, so you can eliminate something that you don't know. All of the weight of an object acts at its center of mass, and the sum, basically, if it's in static equilibrium, the quickest way to write all this garbage here, the more efficient way, what I should have done, is the net counterclockwise, the net counterclockwise torques should equal the net or the sum of the clockwise torques. Right? Everything trying to spin it one way needs to equal everything trying to spin it the other. That's probably the best statement I should have made earlier on here. But not bad.